So in the last lecture, we have come up to the end of the chapter, that is sets. First, all of you tell me whether you have solved yesterday's assignment.
Yes, ma'am.
And have you uploaded it?
Yes, ma'am.
Okay. Any issues there in that assignment? Any difficulties there? Yes.
There was a last question of proving that A into C is a subset of B into C. So that
Okay.
I did find difficult a bit.
Okay. Could you be able to solve that?
We were able to solve, but we did not know the proper answer.
Okay. I will see the question. Just a minute. If A is a subset of B, okay? Seventh one. Seventh one.
Yes, ma'am.
Okay. If A is subset of B and C is any non-empty set, then prove that A cross C is a subset of B cross C. Okay. A cross C is subset of B cross C. Okay. Who has solved it? Can anybody show me who has solved it? Means if that is the correct one, we will follow that. Otherwise, I will give the answer. Has anybody solved it? Yes. Or I have to see the try. You can do it with the help of example. Any example you can take, means A suppose subset like 1, 2, 3. B is as B is subset of A, so we can take B as 1, 2, and C is any non-empty set. So C also we can take as 4 and 5. And by taking the Cartesian product, we can prove that A cross C is subset of B cross C. Okay.
Okay, ma'am.
You people have done? Another means others may be there who have solved it. This is one method, means by taking the example also we can prove that. And these type of questions mainly I put it before you because such type of means operations you may have to do for your MCQs. Okay, mainly your exams will be on the MCQs, yes or no? So these will be helpful for you to solve the MCQs. That's why I have given you uh, this type of questions. Okay, though this contains solving of problem and all the things, but they are useful for uh, your MCQs. Okay. Any other issue is there regarding the assignment? Uh, all others are easy one. So shall we proceed? So we have seen Cartesian products of several sets, then cardinality of Cartesian product. Now we will move towards the power set. Now what is the power set? It is a power set includes all the subsets of a given set, including the empty set. The power set is denoted by the notation P of S, and the number of elements of the power set is given by 2 raised to n. Okay. What it is? A power set includes all the subsets of a given set, including the empty set. Power set means what? It includes all the subsets of a given set. Okay, in that empty set is also there. Then uh, the power set is denoted by P of S. Okay, P stands for power set, and it means we are deriving power set for set S. So we write it like P of S, and the number of elements of the power set is given by 2 raised to n. If n elements are there in set A, then in power set 2 raised to n elements are there. Okay, means suppose 2 elements are there in the set A, then power set of A contain 2 raised to 2, that is 4 elements. Okay. Then a set in simple words is a collection of distinct objects. Yes. If there are two sets A and B, then set A will be the subset of set B if all elements of set A are present in set B. Yes, we know it by means by the definition of subset. Okay, A is a subset of B means what? If it is there, A is a subset of B, means all the elements of A are present in set B. A power set can be imagined as a placeholder of all the subsets. A power set can be imagined as a placeholder of all subsets of a given set. Or in other words, the subset of a set are members or elements of a power set. Okay, in other words, what we can say, subsets of a set. Any subset will be there for a set. Those are the members of the power set of that particular set. Okay. For example, let's say let set A is equal to 1, 2, 3. Therefore, the total number of elements in the set 3. Set is 3. Okay, 1, 2, 3 are there. Means total number in this set is 3. Therefore, there are 2 raised to 3 elements in power set. Okay, in power set, how many elements will be there? 2 raised to 3, that is 8. Okay, let us find power set for set A. Set A is here 1, 2, 3. Subsets of A are now this will be there empty set, then 1, a single 1 will be there, single 2 will be there, single 3 will be there. Okay, then taking the group of 2, 1 2 will be there, 2 3 will be there, and 1 3 will be there. And lastly, the set itself is a subset of itself. Okay, the set A is a subset of set A itself, so we can write it like 1 2 3 also. Then what the power set will contain here? Empty set, set containing 1, set containing 2, set containing 3, then set containing 1 2, set containing 2 3, set containing 1 3, and set containing 1 2 3. Lastly, it will contain all the elements. How many elements are there? Can you count from in power set? 1 2 3 4 5 6 7 8. That is 3 elements are there in set A. So power set of A will contain 2 raised to 3 is equal to 8 elements. Okay, all these are the subsets of A. Empty set will be there, taking single, then taking combination of 2, and lastly the original element, original set. Okay, then about cardinality of a power set. The cardinality of a set is the total number of elements in the set. A power set contains the list of all the subsets of a set. The total number of subsets of set of n elements is given by two raised to n elements. So cardinality of power set will be, if n elements are there in the set, then in power set it will contain 2 raised to n elements. Okay, here we can see P of A is equal to 2 raised to n. Here n is the total number of elements in the given set. Suppose set A is 1 2, n is equal to 2. So power set of A, cardinality of P of A is equal to 2 raised to n is equal to 2 raised to 2 is equal to 4. Okay, subsets of A are empty set, set containing 1, set containing 2, and the original set, that is 1 2. So we can say that cardinality of power set of A is equal to 4. Here set, we can see here set A is equal to 1 2 and subsets of these empty set 1 2 and 1 2. Then what are the power set properties? Okay, a power set is a set that has a list of all the subsets of a given set. The power set, which is denoted by P of A with n elements, has the following properties. The total number of elements of a set is 2 raised to n. Yes, we know that n is the number of elements in original set. So 2 raised to n is the total number of elements in a power set. Then second is an empty set is the definite element of a power set. Empty set is there in every power set. Okay, every power set of a particular set will contain, or power set of every set will contain a empty set. Okay, compulsory the first set will be the empty set. Okay, then The power set of an empty set has only one element. That is also true. If the set is empty set and we have to take uh, power set of that set, it will have only one element, empty set. Okay, it will have only one element and that will be empty set. Then the power of power set of set with a finite number of elements is finite. Okay. For example, if set X is B, C, D, the power sets are countable. Okay. Means the set is finite, then its power set is also finite. Okay. If a set is finite, a power set is also finite. Then the power set of an infinite set has infinite number of subsets. For example, set X has all the multiples of 5 starting from 5. Then we can say that set X has an infinite number of elements. Though there is an infinite number of elements, a power set still exists for X. In this case, it has infinite number of subsets. Means what fourth point is, if the finite number of elements are there, then power set is finite. But if a set is infinite set, then its power set is also infinite. Okay, it will have infinite number of subsets. Here it completes our third unit. Okay, it completes our third unit. Then can you recall all these concepts, basic concepts of set theory? In that some examples of sets were taken, then representation of sets, two methods are there, tabular and set builder notation. Then cardinality of a set is the number of elements in that set. And types of sets are there. In that finite set is there, subset is there, infinite set is there, then proper subset is there, empty set or null set is there, then equal sets are there, overlapping sets, disjoint sets, equivalent sets are also there. These are the singleton sets are there, equivalent sets are there, universal sets are there. Okay, overlapping sets and disjoint sets. Then comes the Venn diagram. Then some operations were there in that: union, intersection, set difference, complement of a set, and ordered pairs. Okay, these were there in, and then the very important concept, that is Cartesian product. Its example, its properties, non-commutativity and non-associativity, then operations performed on Cartesian products, then cardinality of Cartesian product, and uh, for these several sets, means Cartesian products for several sets, that this is also here. Okay, uh, that we have seen. And lastly, today we took this power set, cardinality of a power set and properties of power set. Okay, all of you get this? Hello. Now, shall we move toward the next unit? Yes. Or any difficulties you have in the third unit, you can ask. Are there any difficulties? Are there any difficulties? I'm asking again so we can move further. Next unit is relations. Its name is relations. Like sets, it's also some uh, lengthy bits are here. Then we'll see these one by one. Now, what are the relations? Okay. Whenever sets are being discussed, the relationship between the elements of sets is the next thing that comes up. Okay. When we study sets, the very next term we study is relations, because relations are again depending on the sets. Okay. And after relations, functions unit is there. That is also depending on these two units, that is sets relations. Okay. The relationship between the elements of the sets is the next thing that comes up. Relations may exist between objects of the same set or between objects of two or more sets. Okay. One set is taken and in that relation is defined. Relation will be might be with same set, or relation might be there with another sets. Okay. Now, a binary relation R from set X to Y. Okay, from set X to Y. How it is written? Written as X R Y. R in capital in between the two elements. Okay, a binary relation R from set X to Y written as X R Y or R X Y. Okay, R X Y. Here R X Y means what again? R is the relation from set X to Y. From set X to Y. Again, order is here. If the relation is there from set Y to X, it will write like Y comma X. But as we are taking the relation from set X to Y, here it will be R X comma Y. Okay. Is a subset of the Cartesian product X cross Y. Okay. What this relation will be now? It will be the subset of Cartesian product of two sets, that is X cross Y. Again, see here, relation is from X to Y. So X cross Y will be there. If relation from Y to X is there, then Y cross X will be there. This order is very important. In case of Cartesian product also we have seen X cross Y is different from Y cross X. Both are not same. So See here, as the relation is given from x to y, then this r uh, in bracket x comma y or x r y is a subset of the Cartesian product x cross y. If the relation or binary relation, if the ordered pair is reversed, the relation also changes. That's what I told you. If the ordered pair changes, means we take y to x, then the relation changes. Okay, order here matters. We cannot change the order. Okay, then relation or binary relation R from set A to B is a subset of A cross B, which can be defined as A R B. Means what? Yes, A R B. Am I audible to you? Yes. Then, as I told you, X R Y means R is the relation from X to Y. Same A R B. What it will be? Relation R from A to B. Okay. What does it imply? Where A B belongs to R. That is R A comma B. Okay. It is denoted like this. ARB or AB belongs to R or RAB. Okay. Then a binary relation R on a single set A is defined as a subset of A cross A. Okay. What is here? A binary relation R on a single set A means we can define the relation for a single set also, means we can take the relation from A to A. It's not compulsory that we take the relation from one set to other set. We can take a relation on the same set also. Okay. A binary relation R on a single set A is defined as a subset of A cross A. If that relation R is a subset of Cartesian product of two sets, in that case, as we are taking the example of a single set, the subset of A cross A will be the R. Okay. R is where the, yes, where the R is binary relation. Okay. Then for two distinct sets A and B with cardinalities M and N, the maximum cardinality of relation R from A to B is M into N. Okay. Suppose uh, A's cardinality is M and B's cardinality is N, then the cardinality of the relation R from A to B is M into N. Okay. It's a product of M and N. Okay. Then what are the domain and range for the relations? If there are two sets A and B and relation from A to B is R A B, then domain is defined as the set A such that A B belongs to R for some B in B. Okay. Domain will be defined as element of A and range is defined as element of B. Okay. If two sets are there and there is a relation R between two sets, that is RAB, then what the domain will be? The elements of the uh, first set, that is A, will be called as domain, and range of the uh, set will be known as elements of B. Okay. Then by taking the example, we will see if A is 129 and B is 137. Okay. Now we can see with the help of examples. Here two sets are given. A is equal to 129 and B is equal to 137. What the case one will be there? If relation R is equal to, then R is equal to 1, 1. Okay. If we take the relation R, that is equal to. Okay. Now, how that set will be defined there? A is 129 and B is 137. What we have to do here is, again, in Cartesian product, what we were doing, taking the combinations of all the elements of A and B. Here also we will be doing same thing, but according to our relation, we will set the R. Okay. The first element we will take is 1, and we will combine it with all the elements of B. Here we can see here 1 is equal to 1. Is it true? Yes, 1 is equal to 1. So we can take for equal to relation, we can take 1, 1 in the relation set. Okay. Now we will compare all the elements. 1 is equal to 3, false. 1 is equal to 7, false. Then 2 is equal to 1, that is also not true. 2 is equal to 3, not. 9 is equal to 3, no. Then lastly, the element 7. Then 1 is equal to 7, no, it's not there. 2 is equal to 7, it's not there. And 9 is equal to 7, it's also not there. So when the relation R is equal to, then relation set will be 1, comma 1. Okay. Then in that case, what the domain will be? 1, and the range will be 1. Here this one is element of A and this one is element of B. Okay. So what we will write is A is means domain of A is 1, and this range of this relation R will be 1. Okay. Domain and range. Now case 2 will be if we take the relation R less than. Okay. Less than means what? Suppose we are taking supposing means A is the set element of set A and B is the element of set B. Then what we have to take the relation is A less than B. Okay. Here also we have taken A is equal to B in the case 1. Now case 2 we will have A less than B. Then R is equal to what the R will be, comparing all the elements now. 1 is less than 1, no, false. 1 is less than 3, yes. 1 is less than 7, yes. Then considering 2, 2 is less than 1, no, it will not be there. 2 is less than 3, yes, it is there. So it will contain this element 2, 7. Firstly, it will contain 1, 3 and 1, 7 also. 1, 3 and 1, 7. Now 2, 3 it will contain. Then 2, 7. 2 is less than 7. So it will also contain 2, 7. Okay. Now considering the third element, 9. 9 is less than 1. No, it's not true. 9 less than 3, 9 less than 7. It's not true. So what the relation are when A less than B is there? Then 1 3, 1 7, 2 3, and 2 7. Okay. Now what will be the domain of this one? A चे एलिमेंट्स कुठले कुठले आहेत यामध्ये? 1 2. Okay. So domain of R will be 1 and 2. Range of R, what it will be? Range of R, elements of B from this set. 3 is there, 7 is there. 3 is reporting, 7 is also reporting. So only 2 elements will be there in the range, that is 3, 7. Okay. Now the third, what the third condition taken is A is greater than B. Okay. Element of A is greater than element of B. What will be there? That we have to write it now. 1 is greater than 1. No, it's not true. It won't come here. Then 1 is greater than 3. No, it will not be there. Then 1 is greater than 7. It's also false. It won't come here. Then we'll consider the second element of A. That is nothing but 2. Now we'll consider 2 is greater than 1. Yes, it's true. So we'll take that element, that is 2 is less than 1. Okay. 2 1 will be the pair. Then it has done. Then 9 is greater than 1. Yes, it is. So 9 1 will be here. And 9 is greater than 3. So 9 3 will also be there. And 9 7. Okay, the third element, that is 9 7. It's also means A is greater than B. So we can write it here, right here like this is 9 1 9 3 and 9 7. Okay. Then domain of R, what it will be? Domain set of A. What the domain will be? 2 and 9. Okay. And what the range will be? 1 3 and 7. Okay. Because 1 3 and 7 are the elements of B. So range of R will be 1 3 7 and domain will be 2 and 9. Okay. All of you got this one? Domain and range. Then comes the inverse of relation. Okay. Inverse of a relation. If relation R is from set A to B, inverse relation is from set B to A. Okay. If we define the relation R from set A to B, then what it will be? Inverse relation is from set B to A. Okay. Then the inverse of a relation is formed by interchanging the components of each of the ordered pairs in the given relation. Okay. Uh, what is there in a relation? Okay. In the relation, there are also some pairs. Okay. Those are the pairs of okay, A and B. So what we are considering the inverse as, suppose relation is from A to B, then inverse relation we consider from B to A, and in that case what we do is, relation is nothing but ordered pairs, and in this case what we do is change the order of the pair. If inverse relation is there, suppose M comma N is the ordered pair for where are we? Here we can see. We'll see this example first, then we'll go for the next. components of each ordered pairs. M comma n is suppose there in the set relation set. Then what we will do is we will change the order of the ordered pair, means m comma n is there, we will take it as n comma m. Okay, here the relation given is like this: 1 2 2 4 and 3 6. Then how the inverse relation will be written as 2 1 4 2 and 6 3. Like it will be like this. If we interchange the first and second components, the x and y values of each of the ordered pairs in the relation, we have 2 1 4 2 6 3, which is inverse relation. Okay, as I told, m and n, in terms of m and n, ordered pair contains m comma n in the relation, then inverse relation it will contain n comma m. Like here the relation set is given 1 2 2 4 3 6. The uh, inverse relation will contain the elements as interchanging the ordered pairs: 2 comma 1 4 comma 2 6 comma 3, like this. Okay, next is types of relations. Okay, we can complete types of relations. Types of relations are, in first is empty relation. Okay, a relation R on a set A is called as empty if the set A is empty set. Okay, if the set is empty set, then the relation on that set, it will be the empty relation. Okay, the next is full relation. What the full relation is now? A binary relation R on a set A and B will be called as full if A cross B. Means what? Suppose the relation set contains all the elements of A cross B, that is Cartesian product of A and B, then that relation will be known as full relation. Okay. Relation set is subset of Cartesian product. Yes or no? It is there. So if the relation contains all the elements of Cartesian product of two sets, then the relation will be known as full relation. Empty relation means what? If the set is empty, then the relation is empty relation. Full relation means what? The relation set is containing all the elements of Cartesian product of two sets, that is A cross B. It will be known as full relation. Okay. Next is reflexive relation. Okay, reflexive relation. In that, a relation R on a set A is called reflexive. Okay, if a relation R on a set A is called reflexive if A comma A is, means that ordered pair A comma A belongs to R, holds for every element of A in set A. That is, if set A is equal to A comma B, then if the relation is containing this type of elements, A comma A, B comma B, then it is the reflexive relation. Here we have seen here this 129 and B is 137. If we take A equal to B relation, then R is equal to 1 1. It is containing this type of pair. So this relation will be known as reflexive relation. Okay, this type of relation is known as reflexive relation. Next is irreflexive relation. It is opposite of this one. Okay, reflexive relation contains AA, BB. Okay, an irreflexive relation, here no A comma A, that is no AA ordered pair belongs to R, holds for every element of A belongs to capital A. Capital A is the set. Okay, here A, B we are taking, and R is suppose A, B and B, A. It is irreflexive relation. Okay, it is irreflexive, but the relation contains A and B, B. For all the elements of A, it should be there. In case of reflexive, suppose A, comma B, comma C, three elements are there. Then the relation should contain A, B, B, C, C to be the reflexive relation. Okay. For the reflexive relation, it is also means it's not same. It's exactly opposite of reflexive relation. It won't contain the elements like this A, B, B. It will have different elements A, B, B, A like this. Okay, it will be the irreflexive relation. Then it comes the symmetric relation. What is there in symmetric relation? A relation R on a set A is called symmetric if BA belongs to R holds when AB belongs to R. Okay. Uh, Here AB belongs to R. Such means BA and AB means ordered pairs are switched here in symmetric relation. Suppose 4, 5 is relation is containing 4, 5, then it should contain 5, 4. If 6, 5 is there, 5, 6 should also be there for a set 4, 5, 6. Then it is symmetric. Okay. For every element of the relation, there should be reverse ordered pair. Okay. 4, 5, its reverse order is 5, 4. 6, 5, its reverse order is 5, 6. So this relation will be known as symmetric relation. Okay. Then next comes is the antisymmetric relation. See here, antisymmetric is not opposite of symmetric. Okay. So, the ninth point. If asymmetric relation is there, then it relation R on set A will not contain the element like BA and AB. Okay. It is asymmetric, means we have seen the reflexive, irreflexive. Symmetric, asymmetric is there. Antisymmetric is different one here. What antisymmetric is, we will see here. A relation R on set A is called antisymmetric if A comma B belongs to R and B comma A belongs to R, then A is equal to B is called antisymmetric. Okay. That is, the relation R is equal to A comma B such that A comma B belongs to implies R such that A is less than or equal to B is antisymmetric since A is less than or equal to B and B is less than or equal to A. It implies A equal to B. See here the condition. If we write like both are true, A is less than or equal to B and B is less than or equal to A, will it be like A equal to B? Yes. A is less than or equal to B. Okay. It is there, means A is smaller than B. It's either smaller or equal to. Okay. And in the next, what it is saying, B is less than A, less than or equal to A, means B is smaller than A or it is equal to A. Okay. At the same time, it won't be there that A is less than B and B is also less than A. Will it be there? Yes. For both, if we consider, it won't be at the same time that A is less than B and B is less than A. Okay. So what condition remains is only A equal to B. Both are same there. Okay. And if this type of relation is defined in the relation set, then that antisymmetric, that type of relation will be known as antisymmetric. Okay. This one, eh, the given condition will be A is less than or equal to B and B is less than or equal to A. At the same time, for this, the given scenario is A equal to B. Okay. A relation R on a set A is called antisymmetric if A comma B belongs to R and B comma A also belongs to R. Then A equal to B, what we are writing is A equal to B. Both are there in the relation AB and BA. Okay. And if A equal to B is there, then it will be known as antisymmetric relation. Okay. Because here we have seen both cannot be less than each other at the same time. A is less than B and B is less than A. It won't be there for the uh, uh, same scenario. So what we can write it like as A equal to B. Then next is transitive relation. What transitive relation is? A relation R on a set A is called transitive if AB belongs to R and BC belongs to R, then AC also belongs to R. Okay, for all ABC in A. Example here given is R is equal to 1, 2, 2, 3, and 1, 3. Okay, then what the uh, here relation, it will be transitive. Why? Because 1, 2 is there, 2, 3 is there, and from that we can write it like 1, 3. Okay. If this is the case there in the relation set, then that relation will be known as transitive relation. Okay. How transitive it is? Relation 1 to 2 is there. Then relation 2 to 3 is there. And lastly, it will contain 1 to 3. Okay. The relation, it will be 1, 3. Okay. This is the transitive because A is related to B, B is related to C, then A is related to C. Okay, it is the transitive relation. And lastly, what we'll see is the equivalence relation. What is the equivalence relation? A relation is an equivalence relation if it is reflexive, symmetric, and transitive at the same time. Okay. If three properties are there, those are uh, possessed by the relation, then that relation will be known as equivalence relation. Okay. How, what the example given here is, we will see A is equal to 1, 2, 3. Okay. And relation R here defined is like 1, 1, 2, 2, 3, 3, 1, 2, 2, 1, 2, 3, 3, 2, 1, 3, and 3, 1. Okay. On set A is equal to 1, 2, 3. Now we will see one by one for the properties. For reflexive, what is important? Each element ordered pair should be there, like 1, 1, 2, 2, and 3, 3. Is it there in the relation? 1, 1, 2, 2, 3, 3. Yes, it is there in the relation set. Then uh, what symmetric? We will see for the symmetric now. 1, 2 is taken. For 1, 2, reverse ordered pair is 2, 1. It is there in the relation. Then 2, 3, 3, 2 is there. And 1, 3, 3 1 is there. Okay, so this relation is reflexive and symmetric. Okay, then what about the third, that is transitivity? What we take for transitivity is 1 2 relation is there, 2 3 relation is there, then 1 3 should be there. So here it is 1 comma 3. Okay, got this one? The three properties that should uh, possessed by the relation R. Okay, here it is given by first three, the reflexive property gets satisfied. Then 1 2 2 1, 2 3 3 2 1 3 3 1. It denotes that the relation is symmetric. And for transitivity, what is there? 1 2 is there, 1 to 2 is there, 2 to 3 is there. So 1 to 3 is also there. That is 1 to 3. Okay. Then on it will be on set A 1 to 3. Okay. This is the equivalence relation as it satisfies or a reflexive, symmetric, and transitive properties. Here we have seen this R on this set A 1 2 3. We can see here that it is reflexive also, symmetric also, and transitive also. Okay, getting up to this. Yes, it's already 11:32. So we will stop here today. We have seen uh, these one, what are the relations, then what are the domain and range for relations, some examples depending on that, then inverse of a relation and types of relations. The next uh, session we will be starting with these properties of binary relations. Okay, we'll stop here. How many participants are there? 17 participants. Good enough. All are present. Okay.